Okay, onwards with Faraday's law, more examples. Let's say you have a long conductor with current I flowing in it, and you've got a loop, okay? So that you have, the loop width is, just say, A, and the loop length is B, okay? And what I'd like to do now is, as a first step, calculate the magnetic flux in this loop from this current I. So now we're getting into something interesting here, in that this current I is going to create a magnetic field, and that magnetic field is going to, well, look like what? It's going to look like this here, right? And what does the magnetic field look like near a long current from Ampere's law, from whatever, right? It's going to drop as a function of R, right? And it's going to get smaller here, smaller, 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 okay? Oh, this is B. This is B external, or B from that, you know. What does it look like if we want to calculate the flux going through this area? You know what, folks? Pause this video for a minute and calculate the flux, right? See if you can come up with a proper value for this flux. So what I'm going to do is, the field changes. So how are you going to do this? The flux is the integral of V dot dA, always, right? So B is, the magnetic field here is going to have a certain value. And that's going to depend on how far you are from, let's call this distance x if you want, okay? And this has width dx, right? And the magnetic field is B. What is B equal to? Well, B is equal to mu naught I over 2 pi x. And what is the flux? D phi, okay, is equal to mu naught I over 2 pi x times dA, okay? The angle, luckily the angle is what? The angle between the area and, you know, the angle of the field is 0. So this is going to be mu naught times what? This is B times dx. So what is the flux then? The flux is the integral of d phi. Phi magnetic is the integral of mu naught I over 2 pi x multiplied by B dx. So you have, and x varies from what to what? X varies from, let's call this distance, we have to call this distance C here. Okay, we haven't called it anything yet. So it varies from, x varies from C to C plus A, C to C plus A, and then you get that this is mu naught I B over 2 pi ln of C plus A divided by ln of C plus A divided by C. Okay? All right. What we're going to do next with this example is, okay, how does it relate to induction? So we got this loop here sitting in there, and what we're going to do is, right now it's static, nothing significant, flux going in. What you're going to do now is grab this loop and pull it in this direction at speed v. And what is that going to do? Well, that is going to take you from higher field to lower field. The area is going to be the same. How is this going to change the flux in the loop so that you end up with electromagnetic induction, right? So how is this flux going to change as I, allow this loop to move? Okay, we have to change some things in this expression, right? What is changing in this case? A is the same, B is the same, but now we have to make a slight change again in that this is variable, okay? This thing here is variable, and this is x, right? We're calling this x now, okay, or y, whatever. And now, can you pause for a minute and see if you can obtain a number, a value for the induced EMF, okay? Talking about magnitudes only. I'm not talking about signs right now. Okay, so pause this video and see if you can do that. All right, folks. So epsilon induced is negative d phi magnetic by dt. We're just looking at magnitudes right now. Okay, So there's a negative there. But how do you do this now? Well, remember that we need to parameterize this in terms of, this was C, distance C, but now this is a variable. So how is this gonna, so that looks like what now? D by dt of the following, d by dt of mu naught I b over 2 pi ln of, well, x plus a over x, okay? And how are you gonna do d by dt of this, right? I will leave some of this for you, and some of it is done in the notes, but it's a good example to look at, right? What is constant in this case? Well, this is going to be mu naught is constant, I is constant, b is constant over 2 pi, and then now d of ln of x plus a over x by dt, okay? The trick is how you're going to do this derivative. Well, there are two ways you can do it. You can, I will leave this with you, okay? You can change, path one is change x to vt and take the derivative of this expression, which is going to take some doing, right? And take d by dt. Or you could do, path two is do what? What is d by dt? Keep in mind, d by dt is the same as d by dx times dx by dt. So following the chain rule, you could take d of that by dx, and what is dx by dt? Well, what is x equal to? This thing is moving at speed v. X as a function of time is going to go as what? As v times t. So please take a minute to either replace x with vt here and take the derivative and see how that works out for you, or do the chain rule. And this is really nice. Why? Because do d by dx, you're done with that, and this guy is nothing. What is dx by dt? Is nothing but v, and you can plug it in there, and you can figure out what the result will be. Okay, we're going to pause here. Again, I'm expecting you to finish this. Go look in the notes. It is done somewhere. If you really need to, but I don't think you should. I think you should just do it. It's just a matter of derivative, derivation, differentiation. Okay? Okay, we're done for this little bit, and we'll continue shortly.